Last when we left off, we were graphically adding vectors. That was adding vectors tail to tip to find a resultant. What we can do is an example like we have here, where you have vector A added to vector B to give us vector C. A lot of you already see the relationship here, that this is a 3, 4, 5 right triangle. Instead of going 3 kilometers east and 4 kilometers north, you could just take the straight path of 5 kilometers in the northeast direction at a certain degree. When we combine vectors using their components, their pieces, we can find resultants using just some trigonometry. So a component, each vector can be split into its x and y components, basically pieces that are parallel to the axis. What this means is that we can have components equal 0, but the vector does not have to equal 0. What do I mean by that? If we have a vector on the x-axis going straight out, we could say it has magnitude 1, 2, 3. Let's say this vector A has magnitude 4 meters east. If I was looking for the components of vector A goes 4 meters in the AX direction, but in the Y direction, it goes 0 meters. There is no height to that vector. It's just on the x-axis. When we write these vectors, a vector can have a component equal to 0, but the vector does not have to be 0. So you can see A actually has a magnitude, but one of its pieces actually is 0. When we have more than one vector, what we're going to do is we're going to break each of the vectors into its pieces, its components. We're going to find all its x and y components, and what we can do with those x and y components is use them, just like we did in the treasure hunt, to find the result. If you look at these two vectors here, we got vector A, and you can see the angle there, theta 1. If you're looking for this AS, the piece of A that is in the direction of S, that is the adjacent side of the right triangle. So all I have to do is take the magnitude of A, multiply by the cosine of that angle. Here's a vector again, labeled A. Vector A is going to be off in the first quadrant. So it has a horizontal piece and a vertical piece. So there is an AX and an AY component to this vector. The Y component, if you look, deals with the opposite side and the hypotenuse. And the X component deals with the adjacent and the hypotenuse. And based on SOHCAHTOA, we know that the X component is going to deal with cosine and the Y component is going to deal with sine. I'd say 90% of the time, the Y component usually always is sine and the X component usually cosine. But there is that 10% where you do have to worry about looking at your angle and seeing which side of your vector is actually the adjacent, which one's the opposite. So just be careful. So in this one, they've got a vector that is 2 kilometers long with a 30-degree angle. We want to split that into its two components. Align and draw it right on my x-axis. That would be my A sub x, indicating that's my x component. And I have a vertical piece here. That's my A sub y. So if I wanted to solve for those, well, I know the angle, I know the vector is 2 kilometers long, so what I can do is I can take, for the AY component, the magnitude of A, and since AY is opposite, I'll just do sine of theta. Since theta is 30 degrees, that's a nice common angle. 30 degrees is going to give me half. So half of 2 is going to give me 1 kilometer. So AY is 1 kilometer tall. Now I've got two pieces of my right triangle. If you don't want to do trig again, you can simply just do Pythagorean theorem to solve for AX. But if I'm going to use trig for AX, all you have to do is AX, the cosine of theta. If you do the math on that, so cosine of 30 is about 0.87 multiplied by 2 gives me an AX component of 1.73. So instead of going 2 kilometers at 30 degrees, you could have just gone 1.73 kilometers to the west and 2 kilometers to the north. Or I could indicate west as negative, like we did by our song today. See, in this picture here, vector A plus vector B does give you vector C. But as you can see, we've broken vector A into x and y components. There is the x component of vector A. Here is the x component of vector B. If I want to get CX, CX is just going to be AX plus BX. And over down on this side, you can see that here is the y component of vector A. Here's the y component of vector B. And to find CY, it's just the combination of AY and BY. Once you have CX and CY combined together, you can use CX and CY to create the last right triangle that you need here and here to give you your legs to solve for the hypotenuse of C. And not only that, you can also solve for the angle right here. Like I said, web assignment is going to look for that angle between 0 and anything counterclockwise will be positive. Looking at this, you can break up A and B into their equal components. Just to show you where I would drop those legs to break up those components. So the way I would do this is I would have this blue dashed line be AX, this one up here be AY, and then I would break vector A into its 2 components. I will use green to indicate that I can do this green line to be BY, and I'll go straight over to get AY. And it looks like I'm going to be adding AY and BY, and I will be subtracting AX and BX. One last thing with vectors is that vectors do not have to just be in 2 dimensions. They don't have to be horizontal and vertical. And we live in a 3-dimensional world. We can go left and right, we can go up and down, but we can go forwards and backwards. So technically, you can have a vector that points in all 3 directions at once. It can point to the right, it can point up and out, like that 3-dimensional drawing showing you down below. A unit vector is a dimensionless vector, magnitude 1, that points in the direction of your vector. And to indicate which component we have 3 little symbols that we use for the x, y, and z plane. It's the I, J, K. So if you look up at the top there, I see I, J, K. I is in the x direction, magnitude 1, no units. J in the vertical direction, magnitude 1 again, no units. And K in the z direction, magnitude 1, no units. If a vector is written in IJK format, the problem is it's already broken into pieces for you. You don't have to do any of the trig. So like we combined AX's and BX's, all you have to do is combine all the I's. So if it had something going 3 meters I plus 4 meters J, you cannot add those because those are in 2 different dimensions. But if you had 3 meters I plus 4 meters I, you could get 7 meters in the I direction. Just like the AX, BX, CX could be combined, you can do the same thing with IJK format. So try to show you some examples of that. So like you can see here in example 13 in the WebAssign, vector A is 5.9 in the I direction, 4.0 in the J direction. Vector B, 3.1 in the I, 7.4 in the J. And vector C, 8.7 I, 6.1 J. If I just wanted A plus B plus C as my resultant, I could add the 5.9 in the I to the 3.1 in the I to the 8.7 in the I and get a total I value. And I could take the 4 in the J, the 7.4 in the J, and the 6.1 in the J and get a total Y component. Once I have the two pieces, do your Pythagorean theorem to get the hypotenuse, and then some trig to find your angle. So that's what you're going to be asked to do. That I can show you here is in this simulation. I can grab vectors and put them wherever I'd like. And when I do this, if I have a vector straight in the horizontal direction, you can see it has a magnitude of 16, no angle, because it isn't off the x-axis. There is no y component. I'm strictly walking 16 straight out. I can also take that vector and take it straight up. If it's straight up, the vector is 16 units at 90 degrees. The x component is 0, and the y component is now 16. If I want to put this vector at an angle, now the simulation may not let me give me exactly 16, and it doesn't look like it's going to. You can see with this, if I go out 12 in the x direction and 11 in the y direction, combining those through Pythagorean theorem will give me 16.3 as the resultant and an angle of 42 degrees above the horizontal. You can see I can project those components down onto the axes if you'd like, but the cool thing that this will do for us here is I can take another vector and add it to the first one. Vector 2 has a positive horizontal piece and a negative vertical piece. That's what you can see with Rx and Ry up there. If I look at the components again, there they are. And the components look just like your treasure hunt. The components are just east, they are north, they are south, they could just be west. You don't have to worry about all the angles that original vector gave you. So knowing a vector and breaking it into its components allows you to show and calculate the sum. So the resultant of vector A plus vector B here is that green vector C. And if I put on the style for the component pieces, you can see that AX and BX combine to CX, AY minus BY give you that little piece right in here for the resultant Y component. So the resultant is the combination of the X and Y pieces.